Welcome to class number 8, session number 2. This lecture will focus on sensing mechanisms for metal oxide gas sensors. It's widely accepted nowadays that the gas sensing mechanism of semiconducting metal oxide gas sensors arises from gas adsorption phenomena that lead to charge transfer between the sensing layer and the surface adsorbents such as oxygen adduns. In air, we have an equilibrium coverage of electronegative oxygen adduns that lead to surface band bending as shown here on the slide. Consequently, the conductivity of N-type sensors decreases with respect to the bare surfaces. This conductivity level sets the baseline level of the sensor. When the sensor is exposed to reducing gases, such as hydrogen or carbon dioxide, these gases interact with oxygen adduns and remove them from the surface. As a result, the surface band bending becomes smaller and the conductivity increases. The situation is reversed under exposure to strong oxidizing gases such as nitric oxide or nitric dioxide or chlorine, which form deep acceptor levels at the surface. Consequently, the surface band bending increases and the conductivity decreases. In the next few slides, I will describe very briefly two models developed by Professor Avner Rothschild from the Technion, aiming at providing better understanding of these processes and how they affect the sensor's response properties. The first model regards the effect of chemisorption on the electronic properties of the semiconductor surfaces. This is actually a numerical model that solves this chemisorption isotherm in concrete with the charge balance equation between the surface charge and the space charge in the depletion layer adjacent to the surface. I will not be able to go over the details here, but I would like to note that this model enables to predict the effect of chemisorption on the surface charge density and the surface band bending as function of gas pressure, temperature, and doping level using only physical properties that characterize the interaction between the solid and the gas phases. The most important parameter here is the energy level of the surface adsorbents. In this context, I'd like to draw your attention that researchers treat species as unoccupied and occupied surface states, respectively, and calculate their fractional coverage using the Fermi-Dirac distribution function. However, it's important to notice at this point that due to the surface band bending, which obviously depends on the coverage of charged species, their binding energy is not constant, but is rather implicit function of the coverage. Therefore, the conventional Langmuir model fails in this case, and you shouldn't use it when you deal with semiconductors or with semi-insulators. The other model that aims at better understanding of the metal oxide nanostructures targets the effect of grain size on the sensitivity of the mesoporous thick films. Based on the mechanism described in the previous slides, it has been shown that sensitivity of metal oxide sensors increases dramatically when the grain size becomes comparable to the depletion length, but there is no model that could explain these results quantitatively. It has been shown that the sensitivity of such sensors increases dramatically when the crystallites are smaller than 2 times of the depletion length. In this case, the conductive core regimes vanishes and the entire crystallite becomes depleted of mobile electrons. In other words, all electrons are trapped at the surface states. This situation gives rise to markedly enhanced sensitivity to variations in the density of these states due to the interaction with the gas phase. In order to examine this effect quantitatively, researchers calculated the effective number of free carriers in the limit of fully depleted grains as a function of surface trap density using this integral equation, which simply follows from charge conversion. So the researchers calculated sensitivity, which is simply the ratio between the effective carrier concentrations for slightly deficient and fully saturated surface trap densities as a function of the grain size. The presented graph shows the calculated sensitivity for a tiny change in the surface trap density by only 1 ppm. You can see that this seemingly insignificant difference is amplified by many orders of magnitude and gives rise to large variations in conductivity by a factor of 130 for 5 nanometer grains. Taking in mind that much smaller signals can be measured and you can easily detect variations in conductivity in single percentage level, you can realize that much smaller differences in surface trap densities are still detectable. So, the take-home message here is that nanoside sensors are extremely sensitive to gas-induced variations in the surface trap density. Considering that the detection limit of the state-of-the-art sensors typically lies in the 1 ppm range, it appears that we are far away from tapping into their real potential. Indeed, you will see later that ultra-sensitive sensors have been developed and that can detect sub-ppb levels, and I believe that there is plenty of room for further improvements in this field. There are a few ways to enhance the sensing mechanism of metal oxide nanostructures. One of these approaches is based on loading of small amount of noble metals such as palladium and platinum on metal oxide structure such as tin oxide, because these metal oxides can promote gas response. In this case, sensing is improved by electronic interaction of the palladium oxide and the tin oxide materials. In the described case, palladium oxide is a strong acceptor of electrons and extracts electrons from the oxide. As a result, the loading of the palladium oxide into tin oxide increases the electrical resistance. On the other hand, when palladium oxide is reduced to palladium on contact with the reducing gases, the resistance decreases by back electron transfer from the palladium oxide to the tin oxide. The difference in the electric resistance of the tin oxide induced by a change in the oxidized and reduced states of the palladium is often large, thus giving rise to large increase in the response to the reducing gases. It should be noted that the catalysts not only create enhanced sites for gas molecular adsorption, but also lower the activation energy required for sensing reactions to take place. Altogether, these effects enhances response of sensors. After we have learned the main or rough principles of metal oxide sensors, I will present here an example of such sensors. The example is focused on resistive oxygen sensors for monitoring oxygen levels in lean burn engines. These sensors are based on semiconducting oxides such as cobalt oxide or titanium dioxide, that change their resistivity due to the interaction between point defects and oxygen molecules from the surrounding gas atmosphere. These sensors offer an attractive solution in terms of wide range of sensitivity, simple design, and no need for a reference. In spite of their advantages, these sensors suffer from strong cross-sensitivity to temperature fluctuations, as well as stability issues that have prevented their wide application. With the help of advanced nanotechnology solutions, attempts are made to neutralize these effects. A partial success has been achieved, as will be presented and discussed in session number 3 of this class. We reach now the end of class number 8, session number 2. Thank you.